In this video, grade 12s, I would like to do September paper 1, question 5. Another question we battled quite a bit with. Now, this is a work energy question. And to be able to answer it effectively, we need to remember to identify all the forces acting on the object as it goes through its different stages of motion. So the first question, 5.1, state the principle of conservation of mechanical energy in words. It says that the total mechanical energy in an isolated system remains constant. So in symbols, in mathematical equation, the total, so the sum of all the mechanical energies initially would be the sum of all the mechanical energies finally. So in your potential energy and your kinetic energy, they're forming the mechanical energy. 5.2 is the point of concern, so I'm going to work through question 5.2. It says calculate the kinetic energy of the skateboarder at point B. Now, from A to B, it's frictionless. So, in other words, the work done by any non-conservative force will be zero. There is a change in kinetic energy, and there is a change in potential energy as the skateboarder skates from A to B. But the work done by the non-conservative forces would be zero because there's friction, no friction, only the gravitational force. So we go for WNC equals the change in the kinetic energy plus the change in the potential energy. Now you might find the memo tackling it from a different point of view, but I believe in working from basic principles so that we won't be guessing what to do. So the non-conservative work done is zero. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Now, maybe I shouldn't use final and initial. Maybe I should use A and B. So let's do that. The kinetic energy at B minus the kinetic energy at A would be the change in kinetic energy. The potential energy at B would be the final potential energy minus the initial potential energy at A. Now, I take it that the skateboarder skates from point A, so the kinetic energy at point A would be zero. And I take it that the potential energy at point B would be at its minimum height above the ground, so we will take that as zero. From there, we can say 0 equals EKB plus minus 0 plus 0 minus MGHA. So EKB, if we do our mathematics properly, would be equal to the mass of the skateboarder and the skate, everything 55 kilograms times G 9.8 times the height 15. And we get an answer of 8,085 joules. Right, so that's 5.2. 5.3, state the work energy theorem. It's about the net work done on an object will equal its change in kinetic energy. Now, usually when they ask you to state the work energy theorem, the question that follows requires you to use it. It's the same like with state the principle of conservation of momentum or mechanical energy. They expect you to use it after they've asked it. So question 5.4.1 asks for you to use the energy principles to calculate the kinetic energy of the skateboarder at point C. Now, for this, we need to skip the section BC, and to do that, we need to take in consideration that there is a frictional force acting on this object, and if the object is moving up the plane, the frictional force will be down the plane, and they've given the frictional force as 15 newtons. The normal force will not do any work on the object. The gravitational force only the component of the gravitational force parallel to the plane will do work. Right, so there are two forces doing work on the object. It's the frictional force and the component of the weight parallel to the plane. So it's this component of the weight. If we complete the triangle here, it's the red component. That is the component of the weight parallel to the plane. And in that triangle, this angle here forms a 15-degree angle. So the component of the weight parallel plus the frictional force will do the net work on the object. So W net equals the change in the kinetic energy. Now, it's the work done by the frictional force plus the work done by the FG parallel would be equal to the EK at D minus the EK at C. Now the EK at D, the object stops there, so that is 0. Now the work done by the frictional force would be the frictional force times delta x, that is the distance it goes up the plane, times cos. Now it's moving up the plane, but the frictional force is in the opposite direction, so it's at 180 degrees, so it's cos 180, plus, now the component of the weight that is parallel to the plane is mg sine 15. Then we need to multiply that by the distance it goes up the plane, and the parallel component of the force is 180 degrees to the direction of motion. That will give us negative EK at C. If we substitute the values, it's 15 times 10 times minus 1 plus 55 times 9.8 times sine 15 times 10 times negative 1 and that gives us negative EKC. And if you calculate EKC, you will get 1,545.035. You could round it to 2 decimals, joules. Right, then the magnitude of the frictional force along BC that will enable the skateboarder to come to rest at point D. Now, for us to calculate 4.2 or 5.4.2, it's a frictional force only that causes the change in kinetic energy. So W net equals the change in kinetic energy. And the change in kinetic energy in this case would be the kinetic energy at C minus the kinetic energy at B. And both these quantities we have calculated already. The only force acting on the object while it's moving from B to C is the friction. There is no gravity. Gravity is 90 degrees to the motion. So it's delta X. And friction will once again be in opposite direction, so it's 180 degrees. So F times 10 times minus 1 is equal to, now the kinetic energy at C is 1,545.035 minus the kinetic energy at B is 8,085. So if you do your math there, the frictional force will happen to be 653.997. I've got it. So I guess you can round it to 654. I hope you found this video useful. Thank you for watching.